Liquefied natural gas. It is odorless, colorless, non-toxic and non-corrosive. Hazards include flammability after vaporization into a gaseous state, freezing and asphyxia. The liquefaction process involves removal of certain components, such as dust, acid gases, helium, water, and heavy hydrocarbons, which could cause difficulty downstream. The natural gas is then condensed into a liquid at close to atmospheric pressure by cooling it to approximately -162 degrees Celsius. Maximum transport pressure is set at around 25 kilopascals. The gas produced from hydrocarbon deposits typically contains a wide range of hydrocarbon products, which usually includes methane and butane, together with oil, mud, water, and mercury, are removed from the gas to deliver a clean sweetened stream of gas. Failure to remove such acidic molecules, mercury, and other impurities could result in damage to the equipment, corrosion of steel pipes and amalgamization of mercury to aluminium within cryogenic heat. Exchanges could cause expensive damage. The gas stream is typically separated into the liquefied petroleum fractions, which can be stored in liquid form at relatively low pressure, and the lighter ethane and methane fractions. These lighter fractions of methane and ethane are then liquefied to make up the bulk of LNG that is shipped. Natural gas was considered to be economically unimportant wherever gas-producing oil or gas fields were distant from gas pipelines or located in offshore locations where pipelines were not viable. In the past, this usually meant that natural gas produced was typically flared, especially since unlike oil no viable method for natural gas storage or transport existed other than pipelines which required the immediate use by end users of the same gas. This meant that natural gas markets were historically entirely local and any production had to be consumed within the local network. Developments of production processes, cryogenic storage, and transportation effectively created the tools required to commercialize natural gas into a global market which now competes with other fuels. Furthermore, the development of LNG storage also introduced a reliability in networks which was previously thought impossible. Given that storage of other fuels is relatively easily secured using simple tanks, a supply for several months could be kept in storage. With the advent of large-scale cryogenic storage, it was possible to create long-term gas storage reserves. These reserves of liquefied gas could be deployed at a moment's notice through regasification processes and today are the main means for networks to handle local peak shaving requirements. The heating value depends on the source of gas that is used and the process that is used to liquefy the gas. The range of heating value can span plus or minus 10 to 15%. A typical value of the higher heating value of LNG is approximately 50 megajoules per kilogram or 21,500 BTU per pound. A typical value of the lower heating value of LNG is 45 megajoules per kilogram or 19,350 BTU per pound. For the purpose of comparison of different fuels, the heating value may be expressed in terms of energy per volume, which is known as the energy density expressed in mJ, liter. The density of LNG is roughly 0.41 kilograms, liter to 0.5 kilograms, liter, depending on temperature, pressure, and composition, compared to water at 1.0 kilograms, liter, using the median value of 0.45 kilograms, liter. The typical energy density values are 22.5 megajoules, liter or 20.3 megajoules, liter. The energy density of LNG is approximately 2.4 times that of CNG, which makes it economical to transport natural gas by ship in the form of LNG. The energy density of LNG is comparable to propane and ethanol but is only 60% that of diesel and 70% that of gasoline. Experiments on the properties of gases started early in the 17th century. By the middle of the 17th century, Robert Boyle had derived the inverse relationship between the pressure and the volume of gases. About the same time, Guillaume Montan started looking into temperature effects on gas. Various gas experiments continued for the next 200 years. During that time there were efforts to liquefy gases. Many new facts on the nature of gases had been discovered. For example, early in the 19th century Cagniard de Latour had shown there was a temperature above which a gas could not be liquefied. There was a major push in the mid to late 19th century to liquefy all gases. A number of scientists including Michael Faraday, James Joule, and William Thomson did experiments in this area. In 1886 Karol Olszewski liquefied methane, the primary constituent of natural gas. By 1900 all gases had been liquefied except helium, which was liquefied in 1908. The first large-scale liquefaction of natural gas in the US was in 1918 when the US government liquefied natural gas as a way to extract helium, which is a small component of some natural gas. This helium was intended for use in British dirigibles for World War I. The liquid natural gas was not street